Okay. And we're live. Okay, so I had planned on participating in this contest on LeetCode, and well, it was a few hours ago and I wasn't awake then. So what I'm gonna actually do is I am gonna compete in it after the fact using LeetCode's virtual um, contest mode. So basically, it'll be like as if I'm competing in the contest, except after the fact. Um, so I'm gonna do that. Bi-weekly contest number 83. Let's change the song. Oh no, we're good. We're good. This is a good song. Okay, so I think honestly, I'm just gonna jump right in. I don't have anything specific to say. Let me just make sure everything's set up properly here. I think everything's working. Okay, so we're competing in bi-weekly contest 83 virtually, which means not actually. We can actually see over here how everyone did in the real contest. And not super surprisingly, a couple of people were able to solve the entire problem set in less than 10 minutes. I find it extremely unlikely that I'll be able to do that, but I'm going to try to solve as many of the 4 as possible in the time constraints. So here we go. Would you like to start a virtual contest? Yes. Virtual contest started. Okay, so we're in the virtual contest. So let's just go right in. Okay. Starting with the first one. So the best poker hand, you're given an array ranks and a character array suits. You have 5 cards where the ith card has a ranks I, and a suits of suits I. Oh, okay. The following are the types of poker hands you can make from best to worst. The flush, 5 cards of the same suit. 3 of a kind, 3 cards of the same rank. Pair, 2 cards of the same rank. And high card, any single card. Return a string representing the best type of poker hand you can make with the given cards. Oh, okay. So they just give you... I see. So we just have to check for these 4 possibilities in that order. And well, if we don't find any of these first 3, we just return high card because every single hand has a high card. So first, let's just if here, let's solve this one in Python actually. So what we can do is if list set of suits equals suits, we can return a flush. Oh wait, no. If the length of the set of suits, is 1, so if we only have 1 suit, then this hand is a flush hand. 3 of a kind is 3 cards of the same rank. Okay, so the next thing we can do is we can just make a counter for ranks. And then we're looking for if anything in this counter is 3, so How do we get the values out of a counter? Counter.items. Whoa, get the fuck out of here, geeks for geeks. Yeah, we want counter.values. So, because we're just trying to get this one done real quick. So if 3 in c.values return 3 of a kind. Else if 2 in c.values oh sorry, Python, we got a elif, we return pair, and then otherwise down here we just return high card. Use the example test cases. So we got flush, then we got high card, is that right? No, that should be 3 of a kind. Oh, I see. So this actually needs to be if 3 in values or 4 in values. Okay, let's vals equals c dot values. And it's not going to be more than 5, so flush 3 of a kind pair. Okay, so we get that one. So that's just a quick thing you can throw together using set and counter in Python to get a solution to that problem. So next we have the number of 0 filled subarrays. Given an integer nums, return the number of subarrays filled with 0. A subarray is a contiguous non-empty sequence of elements within an array. Okay, so for this input, the answer is 6. That's because each of these zeros is a 0 filled subarray by itself. And then also we have 2 subarrays of size 2. So this one, this is a, I guess you could think of this as like a, sort of like a combinations problem. Like basically we iterate through this input array and we're just trying to look for a set of zeros, sorry, a subarray of zeros all in a row, like the longest possible one. And then the length of that squared would be the number of subarrays within that. And then that's going to be your answer. Let's see. Can the answer be extremely large? Like, do we need to big int this? Okay, well let's write this one in Python again. So we're gonna have for x in nums. We're gonna have like answer is 0, and then at the end of the program we'll return that. And we'll have we'll have like current subarray length. Current length, and we'll just have it at we'll start it off at -1 because we don't even know if we're going to be starting in one. in a subarray of only zeros. So if x equals 0, if x is 0, then we increase the current length. Current length is the max of 1 and current length plus 1. So basically, if it was 0, we make sure that it goes to, hold on a sec, is that right? If the current length is -1, we want to add 1 to it. It's going to take it to 0. So it's the max. Otherwise, it'll just choose this one. Else, if x is not 0, if current length is greater than 0, then we'll just print it, and then we'll set it back to -1. Let's run this code and see what we get. Elif. Okay, so we got 2, 2. So basically, what my code is discovering right now is the length of all the maximal subarrays of zeros, subarrays that only contain zeros. Let's use the example test cases and run it. I think that there might be an issue with the code still. So we got 2, 2, and then we got 3, and yeah, then we didn't get the last one. So we still have the possibility that once we get to the end, current length is greater than 0. So let's run that. And now we're getting what we expect. So we're getting the first 2 console logs correspond to seeing a subarray of zeros of size 2 in the first input, and then another subarray of zeros of size 2 in the first input. Then the next 2 logs correspond to seeing a subarray of zeros of size 3 and a subarray of zeros of size 2 in the second input. And then no more logs after that, because there are no subarrays of size 0, of only zeros, sorry, in the third input. So everywhere that we print here, what we instead need to do is update our answer. So answer plus equals, and now we need to know, now that we know what all the maximal subarrays of all zeros is, when we have a single subarray of all zeros, what are all the subarrays within that also? And that's going to be all the pairs of starting and ending indices. So it would be for 2, it should be, okay, I think it's going to be curlen squared minus 1. Six 11 0. Okay, it should be 6 9 0 though. So let's think about this. For all of the starting, so let's say that we're dealing with a subarray, and it's got 3 zeros in it. What are the possibilities here? it's gonna be this one through the end, this one, and this one, and then each of them individually. So that is the number of combinations of size 2. So here, let's cheat a little bit. How to calculate number of unique subarrays. Count subarrays, number of distinct subarrays. Whoa. No, that's not what I'm looking for. I'm just looking for the math. I'm just looking for the math on, like, if you have an array of length 10, how many subarrays does it have? So, for example, what I'm looking for is this is 1. This is 3. This is 6. Okay, and what is this? Well, we have 6 here, we have 6 here, and then we have all of them by themselves. Oh no, we have one new one. Is it 9? Hold on a minute. Because oh wait, no, it's at least 12, because we have these 3, right, and we have those 3, and we know that each of those by themselves is 6. Let's just also put the number here. Oops. And then you have (13), 14. Also, this is not 6. Hold on a minute. This is 1. This is 3. This is 1, 2, 3, 1, 2, 1, 2, and the whole thing. That is 6. And this you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, the way I was trying to think about it though was that the number of unique subarrays of an array, you should be able to calculate it pretty easy from the length of the array, because length of the array gives you the number of indices in the array, and then you just want to find all the pairs of those. So it's like, it's going to be n squared because you pair every element up with every other element, including itself. But then it's also less than that though, because like you want to do combinations. Like if I count this element paired up with this element, I don't then want to also count this element paired up with this element. So I kind of want to calculate all the combinations of size 2 and then add n to it, saying that there's also subarrays of length 1. So what's the formula for calculating combinations? It's probably built into Python, right? Okay, I mean it's based on factorial. Is that gonna make my code run too slow? Okay, let's try this. We have from math import comb. And then the answer plus equals the combinations cur length 2 plus cur length. Is that right? How does that perform though? Because factorial is really slow to do if you don't cache the if you don't cache it optimally. Okay, so that generated the answer as 690. So that's actually right. So this math right here is right. We're finding the combinations of size 2, but then we're also taking into account the fact that every single element by itself is also a subarray. But the problem is the numbers dot length could be up to 10 to the 5th. So I might get time limit exceeded on this, but well, I'm gonna try not to risk that happening. So what I'm gonna do is I'm gonna go ahead and oh, did I close the last problem? I did. Let me get that one open again. How is Python math.conb implemented? Because if it has some sort of internal cache of the factorials that it calculates, then we can use this. Otherwise, we have to do that ourselves. Math module in Python contains coefficient binomial expansion. Right. But what's the efficiency? So evaluate here, this is the formula. That evaluates to n factorial divided by k factorial times n minus k factorial. It doesn't say anything about whether or not it caches the factorials that it calculates. Should we assume that it does? How about I just submit the problem? Okay, it does. So, well, it also depends on what the input data was, but yeah, I was able to use Python's built-in combinations math function to generate those factorials without having to do any of the memoization or caching myself, and that got us accepted for that problem. So let's move on to problem 3. So problem 3 is to design a number container system. That can do the following. Insert or replace a number at the given index in the system. Okay, so you got to be able to insert or replace. Return the smallest index for the given number in the system. Okay, so implement the numbers container class. Void change int index int number fills the container at index with the number. If there's already a number at that index, replace it. Int find int number returns the smallest index or -1. Wait. So does this require you to shift stuff around? Like up here, hold on, I'll just have to look at the example, I think, to get an idea. Oh, okay, so very important to note, according to the constraints, the index they give you could be a billion, which means that we cannot use like a vector for this. And at most 10,000 calls will be made. So this is not going to be a like a sequential data structure or contiguous in memory. We're going to end up using something more like a hash map for this, or a hash set. But let me look at this again. So design a number container system that can do the following. You want to insert or replace a number at the given index. Okay, I see. So when it says insert, I thought it meant that like elements in front and behind it may have to like shift around. Well, actually, I assume that the elements after the index would have to move, but they don't. So let's think about this. If we were to have a hash table, then every single time we get a call to change, all we do is we go into the hash table and we insert the number at the index. But we also need to keep track of what the smallest index is for the given number. Okay. So if I change the index, if I change a number at an index, it might be useful to also have a I think the solution might be to have also keeping track of all the indices for the different numbers in like a set. Let's see. So let's decide what our private variables are going to be. So we already know we're going to have an unordered map int, and that's this is just the index to number map. Then what I was thinking is that we would also have an unordered map from int to set of int, where this is number to indices. So let's think about it. In terms of this, every time we come in, every time we get a function call to change, we go to, first check to see if there was already a number at that index. If so, we remove the index for that number from the indices for that number. I don't know if that makes sense. Then we insert the number and update the other set. And then find is as simple as just looking up the indices here and taking the smallest one. I think a set data structure will keep it will keep it sorted automatically, and I think that you just need to grab an element from the front or from the top to get the smallest one. Okay, so let's try to do it. So if index to number how long have I been working on the contest, by the way? Okay. I want to try to keep it realistic-ish because I'm in a virtual version of the contest. I think I started it like 25 or so minutes ago. So let's see how we can do. So we got index to number dot count index. So essentially this function call will return 1 if there's already a number stored at that index. If that's the case, then number to indices number, and then we need to remove an element from that set. Let's see, C++ set erase. I can just give it a value and it will automatically find where it is and erase it. That's what it seems like that does. Erase index. Also, I don't know if this solution is going to work, but if it does, we're already looking at something like an n log n time complexity for this, because of the set operations, which are logarithmic, because a set in C++ is implemented as a binary tree. So we erase that index, then index to number index equals number. And number to indices of number is it just dot insert index? Is that right? So here I got the set open already. It's set insert, and you can insert a value type. Do I need this first line of code? Well, let me think about this. Do I need, let's think about it this way. Do I need anything other than number to indices? Oh, I do, because, hold on a sec. Something here is not quite right. Yes, this is what I need. So, this is supposed to be like this. Like what I was supposed to be doing there that I wasn't doing before was getting the index of getting the number that was already stored at that index, and then going to its indices set and erasing the index. Okay, so that's probably more accurate. After I erase, is there any point actually deconstructing the set? Probably not. So the next thing is to implement the find function, which is the smallest index for the given number or -1. So if number to indices of number dot count. Here, so it's just dot size. If there's anything in that set, then we return the smallest one. And I think it's probably front. I'm not sure, we'll figure that part out. Otherwise, return -1. Sorry, number to indices, number. Okay, so it's okay. So the set data structure doesn't have a front. Can I do star begin? So I got null, -1, null, 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 1, 2. I mean, what am I expecting? Yeah, that exact thing. Okay, let's just go out on a limb here and try sending that in. Okay, that gets accepted. That gets accepted. So the set was a little bit hesitant to tell me what the lowest element in it was, but I got around that by doing star and then begin. And you know what? If I had used hold on, let's see. C++ get smallest element of std set. I think that they probably would have told me to use the max element. Oh, no. Oh, that's interesting. If you do star dot you do star set dot r begin, you get the max. So okay, that actually makes sense because it's not a heap, right? In a heap data structure, you only know what the max or the min is, depending on if it's a max heap or a min heap. But in a binary tree, you would have access to both the max and the min because it's a fully ordered data structure, whereas a heap is, you can consider it just being sort of a partially ordered data structure. Okay, so either way, I'm gonna move on to the last problem of the contest because we got the first 3 already. So this problem is marked as hard. Well, let's just see. I don't know if I'm gonna be able to get it, but I will try. You were given an array roles of length n and an integer k. You roll a k-sided dice numbered from 1 to k n times, where the result of the ith roll is rolls sub I. Okay, so rolls sub I is between 1 and k. Return the length of the shortest sequence of rolls that cannot be taken from rolls. A sequence of rolls of length n is the result of rolling a k-sided dice len times. Note that the sequence does not have to be consecutive as long as it is in order. Okay. Oh, interesting. This is is this a dynamic programming problem? So basically, the sequence has to be in order. Does it have to be perfectly in order, or can there be gaps? Oh, okay, okay. So, for example, it wants them to be consecutive. So, for example, 1, 2, 3, 4 you can do. You can find a 1, 1 in there. You can find a 1, 2 in there. All the way through a 4, 4, you can find that in there. The sequence 1, 4, 2 cannot be taken from roles because there's no 1, 4, 2. I see. That's tricky. I think this is dynamic programming. So one way to think about it, I think, is if we know that all the sequences of length 1 are possible, and we're trying to figure out if the sequences of length 2 are possible. Wait, I'm still a little confused. Why is it looking for 4, 4? Wouldn't it be 3, 4 that it's looking for? What the hell is this song? Moving on. It's looking for... No, I guess it's looking for every single sequence of roles. So like it's looking for all permutations of roles. So let's see. For roles of length 2, it would be looking for 1, 1, 1, 2, 1, 3, 1, 4, but then it would also be looking for 2, 1, 2, 2, 2, 3, and 2, 4. Those all do exist. It would also be looking for 3, 1, 3, 2, 3, 3, and 3, 4. Those do all exist. And it would be looking for 4, 1, 4, 2, 4, 3, and 4, 4. Okay, so this is actually... I honestly think that the explanation here is a little misleading. Oh, okay, I think this line here is supposed to explain it. So basically, the length of the first sequence that is not possible to get. And you're looking for all the different sequences. So this is so yeah, you would, the first thing you would do is you would check your sequences of length 1. Right, well, let's look at the constraints here. So the number of roles is bounded at 100,000. So essentially by binding it, like upper bounding it at 100,000, essentially what they're telling us is that n squared is not going to be good enough for this. You're going to have to do better than n squared. And the same thing for k and like the max size of a role. That's also 100,000. So you also cannot do O of n times k. It's going to have to be something more like n times log k, or n times log n, or k times log k. Any of those would be fine. but you can't have anything quadratic. Essentially, is what these are saying. So I feel like the solution is going to include iterating over the lengths of the sequences, right? Because what you're trying to find is the first sequence that doesn't work. So if you start with sequences of length 1, that's pretty easy to tell whether or not they work. Then if you go to sequences of length 2, you already know that all the sequences of length 1 work. And there's also another thing to keep in mind is there's a best possible way to do each sequence, right? Like so for example, of all the sequences of length 2, I would want, if I was to keep track of that, I would want the ending index to be as far to the left as possible. So for like the 1-1, you would basically, you could keep track, maybe this is just me brainstorming out loud, I don't know if this is right, but you keep track of the fact that the 1 is like already at the end here. So effectively what that means is 1-1, anything else already you can't do it, already doesn't work. Maybe that's an insight that will, like maybe that's an observation that will help solve this more easily. Interesting problem. All right, I'm gonna have to use the restroom real quick, but I'll be right back, and I'll continue to work on this problem for sure. So, one sec, be right back. All right. Where was I? Trying to figure out the hard question from today's bi-weekly contest. And the goal is to find the shortest sequence length that cannot be taken. And so it seems logical to me that the approach to this will include looking at sequence lengths of increasing size, right? So if I start off, and so that way we have, so that's going to be a loop that's going up to k, right? So let's just think about that for a second in the code editor. K is the okay, so K is basically the number of options for each roll sub I. Right. Yeah, that's what it is. That's what it is. We still have our number of rolls, which is separate from K. So we can grab that and put it in N. I think I'm gonna make this K uppercase. And then for int K equals 1, K is less than or equal to K. No. We need to, what's the maximum sequence size? It's N. So we'll have lowercase n represent our sequence size, our sequence length. So it starts off at 1. We'll have it go all the way up to n and increase. Now what would be great is if we could have like, well, obviously we're gonna have a bunch of code in this for loop, but if we could just like return n here, once we figure out that, once we determine that n is the answer, n is the sequence length that you cannot take from the rolls. If we get to the bottom and we don't have an answer, the answer is n plus 1. I don't think that's, no, that's not possible. We're never going to have that happen though. I think this problem is easier than it looks. It's just like wrapping your mind around the kind of the intuition that you need for it. So if we're trying to figure out if we can do all the sequences of size 1, then so I know this is gonna be too slow, but what you could do is in here you could go through all the k's. So int k equals 1, k is less than or equal to k plus k. And so for a sequence of length 1, literally all you're doing is making sure that that the role that you need, which is K, is present. And maybe we also mark where the sequence ends. Here's an idea. What if we restructure this a little bit? I want to think about this a slightly different way. Let me comment all of this code out and just leave it for a second. So instead of doing what I'm doing here, where I'm iterating through all this possible sequence sizes, starting at the smallest sequence size, and then trying to figure out as I'm going up through the increasing sequence sizes, at what point is it no longer possible to make the sequence? What if we did it slightly differently? What if we started off at the maximum roll What if we start off with the maximum roll and we go downwards? And we keep track of where the last point. So basically, I want to store the last instance of K in rolls. I want to store that. So let me just create a data structure real quick where I could store that. Vector of int, I don't know, kpos, which is of size k plus 1. No, it's of size, yeah, k plus 1. The other thing that we could pre-calculate that might be useful for this problem is we could pre-calculate where all the indices of the numbers are. So we could basically create a data structure that tells us that for the number 1, the indices are 2 and 8. For the number 3, the indices are 4 and 5. I don't know if that's right. Wait, actually, is this just completely wrong? It's a tricky problem. Because the sequences, it's like, they could be in any order. So what I was trying to do was I was trying to keep track of where the last element of the sequence was, and then we could know whether or not other sequences are still possible of greater length, because we would know what indices are left after the last element of the previous sequence, and we would be able to know what numbers are available there. And it would need to be one instance of every number, right, for the next sequence to be possible. I might not have what it takes to figure this one out right now. I'm kind of tempted to go ahead and go to the contest discussion and learn from that. We can learn it together, because I did solve the first 3. So I'm doing this contest virtually. And I did solve the first 3 problems. I just haven't been able to get the 4th one yet, the 4th and hardest problem. And part of me is telling me to just pass on, just move on. Okay, let's say that we know all of the sequences of length 2 are possible. Let's say that our code has been running and our code has just verified that. So we know the answer to the problem is not 2. The next thing we need to figure out is the answer to the problem 3, right? Can we form all the sequences of length 3? And so the way to figure that out is you have to consider the end of every sequence of length 2 and ask yourself, are all of the possible roles, do they exist after this index? They have to exist, otherwise you can't form all of the sequences of the next length, of length 3 in that case. So what we could do, what if we were to iterate through the input one element at a time, and at each element where we look at it as if it's the end of a sequence. So we get to 1 and we're like, okay, 1 is the end of, in this case, 1 is the end of 3 sequences. It's the end of 4, 1, 2, 1, and just 1 by itself. Does that help us? Does that help us? Let's go, okay, I've just decided. I'm gonna go have a peek at the discussion section, and maybe if I don't completely spoil the problem looking there, I'll come back and implement it using some of the insight that I get from the contest discussion. Okay, so let's look at this. Is there a hint? Oh, we got hints. Okay, let's look at the hints first. So let's see what hint 1 is. How do you find the minimum index such that all sequences of length 1 can be formed from the start until that index? Yeah. Yeah, okay. And then hint 2 is going to be, what about for length 2, right? Does it show you what the recurrence is? Can you extend the idea to sequences of length 3 or more? Okay, let's try to use these hints. So the minimum index such that all sequences of length 1 can be formed from the start until that index. Then starting from the previous minimum index, the next index such that all sequences of length 2 can be formed, that would just be the next index that enables you, the next index such that you have included the numbers 1 through k again. Wow. Alright, well let's go ahead and take a look at this, because this guy usually tries to provide some intuition and some explanation. For the first number, it could be any number from 1 to k, so my intuition is to check the first occurrence of all the numbers from 1 to k. So that means from A0 to AI we have seen all the numbers once. In other words, A sub 0 to A sub I forms our first complete set, including all the numbers. This complete set can satisfy any number from 1 to k as the first number in the sequence. Okay. Then we continue this process and find out the next complete set. We continue doing this and assume we can find x complete sets in total. There may remain some elements, but the rest cannot form one more set of all the numbers. Okay, that does make sense. Then we can take any sequence of length x. X plus 1 then is the length of the shortest sequence of rows that cannot be taken. Oh my god, that makes sense. Okay. Prove. Assume there are X complete sets in the roles. We can take any sequence of length X. We take any number from a complete set. We can't take all sequence of length X plus 1. We can construct one sequence S that we can't take. S sub 0 is the last element in the first complete set. S sub 1 is the last element in the second complete set. S sub X is one element which is not in the incomplete set after X complete set. Okay. So he's got a little proof. That's nice. Okay. So I just glanced at the code and it's really short. So let me go back and see if I can write it. I understand now. I understand. So, what language should I solve this in? The intuition behind it. See, that's the thing about some of these problems. As long as you can get like the observations, the intuition, you can solve it. But my problem is I got to the problem and I immediately was trying to like construct it like as a DP in my head. It turns out it's not a DP. So let's just solve it in C++. So we'll have unordered set of int s. Then for int I equals 0, I is less than n, plus I. We need to store how many complete sets we've seen. So int number of complete sets equals 0. So the first thing we do is if s dot size equals k. So if we've got a complete set, then we increase our number of complete sets, and we empty out s. How do you empty out C++ clear container contents? Okay, I think we can just do s.clear, right? s.add, s.insert roles sub I. If we get to the end after finishing the whole thing and we still have we have one last complete set, we take it into account, and then the answer is just return the number of complete sets that we saw plus 1. Okay. All right, so that's how you do that one. It ended up being a lot simpler than I thought, but we do get it. Runtime is looking really good. Did no one else solve this in C++? Why am I getting I'm surprised that I'm getting faster than 100% of, or less memory than 100% of submissions. Let's go take another look at the, okay, so it does use OFK space. So now that I wrote my solution, I'm just gonna go and see what it is. So the shortest sequence, so, okay, got it. So they just start off the result at 1. They have the hash set, they go through everything. Every time after they, okay, this is actually a little bit smart of a way to do it. Every time after they add something to the set, the first thing they do is they see if the set's full. If it is, they increase the answer and clear the set. C++, same thing, unordered set. This is what I just did, Python, blah, 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 blah. And then okay, well, as you can see, people are sad in the comments that they didn't figure it out. I'm a little sad too, but it's a good mental I think, you know, even when you don't get the problem right, it's a good mental exercise to go through the process of trying to figure it out yourself. You know, once you put in some brain sweats and you try to figure it out, just go look at what the solution is and try to learn from it. And then, you know, next time you might not need to look at the solution. You'll be able to figure it out yourself. Okay, so that's it for that is it for the contest from this morning that I missed. I'm planning on streaming the evening contest, which is at 7:30 p.m. Pacific time. And yeah. So I am gonna have another stream today where I stream the evening contest. So I think because of that, I will be ending the stream here. It was a little bit shorter, but we just went through the 4 problems from this morning's contest. We got the first 3 fairly easily. The problem 4 we didn't figure out, but we ended up learning how to do it from some other people's solutions and explanations and stuff like that. So if you were here for this short stream, thanks for watching. But I will be back with much more LeetCode on stream. Specifically tonight, I'll be back for the LeetCode weekly contest, and then following that, I'll still be coming back daily for LeetCoding streams. So if you were here, thanks for watching, and with that, send you over to the ending screen, and I'll be back later. Take it easy.